Well, hello everyone. This video reviews the important ideas of Chapter 21, Carboxylic acids and their derivatives. We include in this chapter nomenclature, physical properties, and some of the important reactions of carboxylic acids and their derivatives. Derivatives refer to compounds that can be made from carboxylic acids, and they include acid chlorides, esters, and hydrides and amides. We'll have more to say about those later. What I want to go over now is to review the major reactions of carboxylic acids. And let's begin. As implied by their name, a carboxylic acid is acidic. It's classified as a weak acid, and a weak acid will react favorably with a strong base. And we show that with the equation here. B minus, could say, represents a strong base. It's going to pluck off the hydrogen ion from the carboxyl group, leaving the carboxylate and the conjugate acid of B. Now, it's important to realize, too, is that the conjugate base of a carboxylic acid itself could undergo acid-base reactions. There usually goes with it a metal cation like sodium, or potassium, lithium, that kind of thing. And these are stable compounds, the metal carboxylate compounds. It's an organic salt. So if you took one of these and mixed it with an acid, you're going to get an acid-base reaction, as we show in the second equation here. If HA, of course, is strong, it's going to be a favorable reaction and protonate the carboxylate, converting it back to the conjugate acid of the carboxylate. And so you want to kind of keep that in mind if you when you're taking the quiz. You might see a reaction of a carboxylic acid, which is in fact it acting as an acid. You might see its conjugate base in the equation, and of course there it would be an instance of it acting as a base. An important reaction of carboxylic acids and their derivatives is a kind of nucleophilic substitution. And carboxylic acids and their derivatives undergo this. Basically, what is going to take place is, let's start with a carboxylic acid and see what might happen to it. There is a couple of reactions where the OH is converted to a good leaving group, and then a nucleophile reacts with that resulting compound to produce an overall substitution. Okay, I did pause the video and I wrote in a general formula for a carboxylic acid derivative. The symbol L here, it represents a leaving group in this nucleophilic substitution. It's a heteroatom group, including chlorine, a carboxylate, an ethoxy group, or a nitrogen of an amide. And each of these groups now is subject to displacement by a nucleophile. Now we'll have more to say about the details of this process, especially the mechanism. Now we'll go into more details with respect to the mechanism when we actually work through some of the assignments. But let me just say, this nucleophilic substitution is not an SN1 or SN2. It goes by a completely different mechanism. As we illustrate right here, G can stand for a leaving group. The nucleophile bonds to the carbonyl compound to form an intermediate species, shown here. This is called a tetrahedral intermediate because the carboxylic acid or the derivative, the carbon is a carbonyl group, has three things attached. It's called trigonal. And when four things are bonded, of course, the carbon becomes tetrahedral. This species isn't a stable compound, and what will happen is that in a follow-up step, it will eject a leaving group. In my illustration here, that's given by the symbol G. And that gives you the nucleophilic substitution. So the leaving group gets replaced by nucleophile in two steps. It involves the formation of an intermediate species called the tetrahedral intermediate. Okay, let's look at the next general reaction. Carboxylic acids and their derivatives are subject to reduction. Remember that reduction involves either a gain of hydrogens or loss of oxygen or a combination, and it's basically the opposite of oxidation. Both the carboxylic acid and one of the derivatives, esters, amides, and so forth, are subject to reduction. I'm showing the general equation here, and we'll let L stand for the leaving group. That's either one of the it is a heteroatom group. It could be an OH after conversion to a good leaving group, or the chlorine, carboxylate, and so forth. Reduction is indicated by symbol H in brackets. That's a general generic symbol for reduction. Reduction is accomplished by a reducing agent. We'll have more to say about that. So the carboxylic acid or the derivative is treated with a reducing agent. This gives a product which has some stability. You don't actually isolate it. You generally do an acid workup that converts that product, well, in general, to an alcohol that we're showing here, an alcohol. Now, some of the reducing agents, the ones that are generally representative, would be sodium borohydride or lithium aluminum hydride. As well, hydrogen and a catalyst like platinum, hydrogen gas, would also represent a type of reducing agent. Now, there's a generalization, is that carboxylic acids and most of the derivatives will give, after acid workup, an alcohol. That's what we're showing here. That's very general. But there is an exception to that rule, and that is if you have an amide. Now, amides are the least reactive of the carboxylic acid derivatives. Sodium borohydride is not powerful enough and won't react with it, so you have to use one of the strongest reducing agents. That's lithium aluminum hydride, fits that bill. So if you treat an amide with lithium aluminum hydride, again, you'll get a product that's an aluminate. You don't isolate it, but you do an acid workup. And now look at the final product, though. You don't get an alcohol anymore. What's happening is that the carbonyl group here it gets reduced to a methylene. The nitrogen stays attached. And so the amide is reduced to basically an amine. Okay, now there's another interesting variation of this. It's the reduction of, well, there are two compounds that work here. These are relatively reactive ones, an acyl chloride or ester. These are treated with sterically hindered aluminum reagents, aluminum hydride reagents, the kind of designer reducing agents. We'll have more to say about that when we talk about the exercises. But when these substrates are treated with these special hindered aluminum hydride agents, you don't get an alcohol or amide. Instead, you get an aldehyde, and we'll have more to say about that. And this is, in fact, one of the ways that aldehydes are synthesized. It's a high-yield reaction. Another major reaction of carboxylic acids, not the derivatives, is called decarboxylation. This is an important reaction, and we'll actually see it biochemically. You see it, I think, in glycolysis, and you see it twice in the citric acid cycle. So it has biological importance. Now, this reaction involves basically a carboxylic acid that's activated, that has a spatial group attached at a key position, and we're representing that as this formula right here. This G compound, or G symbol, what's important is that it's attached to the carbon adjacent to the carboxyl group. An adjacent carbon is called the alpha carbon. So this G group we could call an alpha substituent. And there's three possibilities here that we will encounter. As shown here, a carbonyl group, nitro, and cyano group. Now, these three groups are so important. I kind of humorously refer to them as the three amigo groups, because we're going to see them again in a seemingly different reaction in a later chapter. There's an underlying theme to these three groups, and so do pay attention to them. Now, if one of these amigo groups is attached to the alpha carbon of carboxylic acid, and here's what you do: you subject it to high temperature. We're talking 150 degrees Celsius or higher. High temperature, of course, bonds get broken and made, and what we basically do is eliminate a CO2 molecule from the carboxyl group. The hydrogen here attaches to the carbon, and there's two products. Carbon dioxide gas comes from the ejection of CO2 from carboxyl group, and you could say the hydrocarbon type group, where hydrogen takes the place of the carboxyl group. And we'll have more to say about that when we talk about the exercises. All right, let's see. Let's look at another reaction. The final reaction in this series of general reactions of carboxylic acids and their derivatives has a name. It's called the Hell-Volhard-Zelinsky reaction, or HVZ. Now, it applies only to carboxylic acids, not the derivatives. Now, put in proper context, this reaction is important because it's another instance where a halogen attaches to the starting material. It's a halogenation reaction. The key atom that gets halogenated, where the halogen attaches, is in fact the alpha carbon of a carboxylic acid. Remember, that's the next door carbon that we talked about. That is this carbon here, the alpha carbon. A hydrogen attached to that is going to be replaced by a halogen. Now, X, I didn't show an equation, but X is going to be either chlorine or bromine. All right, iodine is not applicable. Fluorine, neither is fluorine, too reactive. So if you take the carboxylic acid and mix it with the halogen, actually not very much happens. But if you add a trace of phosphorus here, a very complex reaction takes place, several steps, and those are outlined in the video and the class notes. The overall result is simple. One of the alpha hydrogens gets replaced by a halogen. All right. Now, I also want to say a word about synthesis of carboxylic acids. There's generally two methods for making carboxylic acids that are, new for us. Carboxylic acids can certainly be made by oxidation of alcohol or aldehyde, and that we've seen in previous chapters. The two reactions I show here are you're seeing in your study you're seeing for the first time in your study, and let me talk about each of these. The first one is converting a haloalkane to an organometallic, either an organomagnesium, a Grignard reagent, or also you could convert it to a organolithium. All right, that organometallic then is treated with carbon dioxide. All right, this is the structure of carbon dioxide shown here. Now, what happens then is hopefully you guys can figure out now. It's what happens is very logical. The carbonyl group, or the CO2 rather, has two carbonyl groups. Carbonyl groups are subject to addition. We just learned that in the previous chapter, chapter 20. Now, if you take the Grignard reagent and write it in its ionic form, I got missing the plus sign on the magnesium though, then what you have basically is it's an addition of the nucleophile, electrophile across one of the carbonyl groups. And so the nucleophilic carbanion is going to attach to the carbonyl carbon, and the magnesium's X positive is going to bond to the oxygen. This gives an ionic compound shown here. It's a magnesium alkoxylate. It's a salt. You could isolate it. Nobody does. What you do is you do an acid workup. In the acid workup, hydrogen ion attaches to the oxygen and produces your carboxylic acid product. The second major way of making carboxylic acids is to start with an organonitrile, something that has a carbon-nitrogen triple bond. That's a nitrile group. And the chemistry is it's subject to hydrolysis. Hydrolysis means reaction with water. So you treat it with water either under acidic or basic conditions. And this is fairly strongly acidic or strongly basic. With heating, you require either the acid or base, and both of them involve heating. Now, I'm not going over the mechanism at this point because some of the steps here involve chemistry we haven't encountered yet, haven't learned. But if you do it under acidic conditions, the nitrile group, there's a series of addition, substitution, eliminations. Ultimately, you get the carboxyl group. There's a whole lot of things that happen. And I don't think, I'm not sure even discuss the mechanism. It's something that won't be on the quiz, as they say. All right, if you treat the nitrile with water and under basic conditions, now here you get the carboxylic acid. Under base, it'll be the carboxylate that forms right here, the conjugate base. What you want is the neutral carboxylic acid, so you do an acid workup. You acidify with acid, indicated by the H plus symbol. All right, those are two, a couple of important ways to make a carboxylic acid, starting with the organonitrile. All right. All right, let's start looking at the assignments, at the problems in the assignments. There are, 6 assignments altogether. Assignment 21.1 deals with nomenclature and physical properties. I think those ideas are fairly straightforward. The physical properties is, at this point, I believe you are familiar with the principles there, and I think you won't have any trouble with that. If you have any questions, of course, do contact me. And then, of course, there's nomenclature. I don't think I'm going to have not going to say a lot about that in the video review. I don't think there's any surprises there or anything particularly difficult. Let's look at the second assignment, chapter 21. You have to give the product of products, organic product of products for each reaction. Now, here's the idea. You want to not cling to memory banks. The idea is that to figure out the course of reaction of the products, decide what reaction type it is. So what you want to do is review the basic reaction types of carboxylic acids and derivatives. That's something I reviewed in my introduction in this video. and then go from there. So that's the kind of thinking I'm going to be using when we tackle each of these problems. So here we go. So we have, okay, in problem A, we have a Grignard reagent reacting with CO2. Now, in addition to the carboxylic acids and their derivatives and the reaction types, keep in mind that there are also reactions for synthesizing a carboxylic acid. Now, in the reactants, we don't see a carboxylic acid or a derivative, and that suggests that we're dealing with the synthesis of, in this case, a carboxylic acid. Moreover, you can kind of deduce that. Remember that when you have a Grignard reagent, you write it in ionic form. And so let me do that now. All right, there we have it. The carbon bound to magnesium is a -1 charge, get a pair of electrons there. And then the magnesium Cl, that part would be positive. That's the ionic form for the Grignard. It's helpful to do that because what's going to play out is this is basically going to provide electrophile, nucleophile, and you look at your drawing, you can see what is obviously the nucleophile and what is obviously the electrophile. So carbon, CH2 is the nucleophile, the nucleophilic carbon, and magnesium plus will be the electrophile. Now, we mentioned this in my intro, that CO2 has, structure-wise, has two carbonyl groups joined together with a common carbon. Carbonyl group undergoes addition. So what's going to play out, of course, is that the nucleophilic carbon is going to attack the carbon, bond to the carbon, and then the electrophile will bond to that oxygen there, followed by acidification. This is going to basically produce a carboxylic acid. So go ahead and write that structure out. And this is the final product after the acid workup. So I'm working selected problems from the assignments. There isn't time to go over every single one. I'm choosing to do reaction C. Next, we have carboxylic acid reacting with sodium hydroxide. Okay, now, obviously, if you see a carboxylic acid or derivative in the equation, it's the reaction of an acid or derivative. So we're going to look for a reaction of carboxylic acid. And remember, we reviewed the types. Carboxylic acid is an acid, can act can undergo an acid-base reaction. It can undergo a substitution where hydroxyl gets converted to a good leaving group, and the leaving group is converted to or is replaced by a nucleophile. It can also undergo reduction, decarboxylation, and alpha halogenation. And the last three, you see, don't apply. So what kind of reaction is it? You've got the carboxyl group, that's an acid, so you can label it thusly. And it's important to realize now that sodium hydroxide is a base. Now, it can act as a nucleophile, but that wouldn't apply here. So this is simply an acid-base reaction, and so you know the pattern there. Just go ahead and apply it. So the carboxyl hydrogen comes off as hydrogen ion, bonds to the hydroxide ion, and so this gives you the sodium carboxylate. Now, I will now write out the structure. And there we go. Sodium carboxylate. Na plus, and then a carboxylate -1. It is a ionic compound or salt. Now we look at reaction D. All right. Do we have a carboxylic acid here or a derivative? Don't see it. Logically, you might follow that this is a synthesis of a carboxylic acid, and I actually realized that can work here. The other way to look at it is HCl is an acid, and the carboxylate is the conjugate base of an acid. And so if you put those two together, that's going to be an acid base, where the carboxylate is the base and HCl is the acid. You have a acid-base reaction. All right, so the HCl donates a hydrogen ion. Hydrogen ion bonds to the O minus, producing the product here, which I'll now write out. Okay, there we go. And this is, if you remember, the name of this benzoic acid, and then sodium chloride is a byproduct. All right, next we look at reaction E. Okay, we have carboxylic acid reacting with PCl5. PCl5 may look abstruse. You may wonder, what is that and what's it doing? But if you think back over your studies, the notes and the videos, well, let's put it this way. The carboxylic acid in the equation means it's a reaction of carboxylic acids. What kind of reactions? Well, they act as an acid. PCl5 is not a base. They undergo reduction. PCl5 is not a reducing agent. They undergo decarboxylation. No, that doesn't fit. That's carboxylic acid with a spatial activating group on the alpha carbon and heat, and that doesn't apply. The only thing that leaves is a nucleophilic substitution. The PCl5 actually converts the hydroxyl to a good leaving group. It's a phosphorus compound. And then the chloride ion acts as a nucleophile that displaces off that leaving group, and you get a acyl or acid chloride. I'll now write out the structure for that. All right, there we go. This is the acyl, or also called acid chloride. The OH group, converted to a good leaving group, gets replaced by the chloride ion nucleophile, and there is our product. All right, let's look at, well, let me look ahead and see what we have here. If there's another problem, we'll do that, or otherwise we're going to go to the next assignment. Okay, this is questions from assignment 3A. There's two number threes, 3A and 3B. They're on the same theme. Let's take a look at these. Gal, you can scan down the different reactants here. You can see that they're all carboxylic acid derivatives except for problem I here, and that's a carboxylic acid. So always look for the types of reactions. If you have a carboxylic acid, remember it might be an acid-base reaction. Look for reducing agent. If you don't see it, it's not reduction, and so forth. One of the major reactions is the nucleophilic substitution. We call that an acyl carbon substitution. Acyl carbon substitution, that's another way of saying a carbonyl carbon substitution. All right, so let's take a look at reaction A. All right, that's an acid chloride. Carboxylic acid derivatives, their major reaction is either nucleophilic substitution or reduction. It's reacting with methanol. That's not a reducing agent, so that would tell us that it must be an acyl carbon substitution. An acyl carbon substitution, there's a pattern here. I talked about that in the video lectures. And I also, of course, talked about the mechanism. The Cl is a good leaving group. That's going to come off. Then it's going to be replaced by the nucleophile, which would be the basically the methoxide ion here. So one comes out, the other goes in, and so you can immediately write the product, which I'll now do. All right, there is the expected product. The Cl coming off, replaced by the nucleophile. The nucleophilic oxygen is what bonds the carbon, so you want to show that in the product. The O bonded to a carbonyl group, in turn bonded to CH3. All right, one question though is, what is the functional group here? What's the class of compound? Or the C double bond Cl reactant, that's an acid chloride or acyl chloride. So we ask yourself, this would be an ester, ester, E-S-T-E-R. That's the name of that particular carboxylic acid derivative. Note, in this reaction, we're showing how you can take one carboxylic acid derivative and convert it to another. All right, I think we're going to say more about that later. Let's look at reaction B. We have an ester. Don't see any reducing agents. So that looks, again, like it's going to be an acyl carbon substitution. Now, the heteroatom group is going to come off and be replaced by a nucleophile. In this case, that would be the OH of water. The H from the water comes off and hooks up with the oxygen. So let me go ahead and write out the product of that now. Okay, you can see the product structure I've just written out. How did I get it? Well, there's a pattern that's followed, and I tried to explain this, of course, in the study materials. The heteroatom group is a leaving group, and it comes off. That's shown here, the OCH3 coming off. The reactant here is going to provide a nucleophile. Water will provide OH as a nucleophile. The H breaks off from the water, and it's going to bond to the OCH3, right? And so following that pattern, we write the structures shown here, carboxylic acid and the alcohol. Now, this in textbooks, this reaction would be classified. Let's think about it. In reaction A, we saw a case of one carboxylic acid converted to another. In this case, we have a carboxylic acid derivative, an ester, converted to a carboxylic acid. So it's a case of a derivative converted to the parent acid, parent carboxylic acid. All right, let's take a look now at the next reaction, reaction D. This is one that can potentially confuse a student. The anhydride, the ones that are always in use are symmetrical anhydrides. Basically, the groups attached to the carbonyl groups will be the same. There does exist anhydrides where the groups are different. Those are called mixed anhydrides, but nobody really uses them. And so those groups attached to the carbonyl groups will be always the same. Thing is really symmetrical. Now the key is with an anhydride, one of the carbonyl groups acts as the electrophile, and the remaining part is the leaving group. So that's what you want to be aware of. Let me kind of mark that here. So this carbonyl group, that's the site of the substitution where the nucleophile attacks. And then you can circle everything else. That's the leaving group. The leaving group, that's the heteroatom group attached to the carbonyl group. That's what's going to break off. And it's replaced by a nucleophile. What's the nucleophile? Well, it would be NH2 from NH3. So you can see that's going to give an amide. Let me go ahead and write the products now. Okay, there we have it. That circled carboxylate, as you call it, the whole thing breaks off. That's a leaving group. It's replaced by NH2, which we show here. And then the piece circled in red comes off, and the hydrogen from NH3 bonds to that oxygen and produces this carboxylic acid byproduct. Okay, I may have made an editor's error here. I'm blabbing away and it's on pause. So let me just back up here on reaction B in case you missed something. It's a acyl carbon substitution reaction. This ester here, the OCH3, is the heteroatom group breaks off, replaced by the OH nucleophile from water, and I have the structure of the product written there. In reaction D, that's an acid chloride. The circled part is the leaving group that breaks off, replaced by the nucleophile NH2, and we have the products shown. Let's the next one is an ester reacting with the anion of the thiol, the sulfide ion. Looks like a acyl carbon substitution. The OCH3 is the heteroatom group, and it's the leaving group. It breaks off, and it gets replaced by the nucleophile. Sulfur is the nucleophilic atom. And I want to make sure you show the new bond between sulfur and the carbonyl carbon. Let me go ahead and write out the products of that. Okay, I've now written out the products of that reaction. It looks like let me pause the video. I destroyed one of the reactants. Just a second. Okay, I drew the sulfur reactant back in. Okay, now look at the next reaction I. Let's see what we have here. We have a carboxylic acid. All right, think about the types of carboxylic acids. Acid base, nucleophilic substitution, reduction. I don't see a reducing agent here. We're going to rule that out. It's certainly not decarboxylation. Acid base, well, the species right here is not really a notable base. And so we're not going to predict an acid-base reaction. What does that leave? Well, acyl carbon substitution. Now the OH, it can come off. It has to be converted to a good leaving group. What happens here is the hydrogen ion acts as a catalyst, will protonate the OH, the carboxyl OH, and that makes it converts the OH, a bad leaving group, into a good leaving group, water. Water breaks off and gets replaced by the nucleophile, the oxygen part of the alcohol. So it is the thing to see is that this carboxylic acid is undergoing an acyl carbon substitution. The OH gets replaced by the nucleophile. And okay, let's see. Let me pause the video for a second. So the OH is the leaving group. The heteroatom group is going to break off. The nucleophile would be shown in the red box here. Nucleophilic oxygen is going to come in, bond to that. The OH breaks off. It's going to hook up with that hydrogen there. That's part of I think I call that the type 2 pattern. So that's going to produce an ester and water byproduct. I'll go ahead and write out the structures of those now. Okay, there we have it. Now think about how this compound would be classified. It's a carboxylic acid derivative, and this would be an ester. Everybody needs to recognize, to be able to classify a derivative, and their derivatives are acid chloride, anhydrides, esters, and amides. Now you can see in the overall reaction would be a carboxylic acid converted to a derivative, name of the ester. Textbooks would call that an esterification of a carboxylic acid. All right, now the next reaction, I think this is the last one that I'm doing in the review. This is called orthophthalic acid. You don't need to know that. It's a dicarboxylic acid, and it's heated. That gives you a hint here. It tells you intermolecular acyl carbon substitution. What's going on here is that one of the carboxyl groups, the carbonyl carbon in that, is the site of the substitution, and the OH would be the leaving group, whereas the nucleophile, well, would be the OH of the adjacent carboxyl group. So let me see if I can sketch some arrows in here to show that. Okay, so let's take this OH as the leaving group, the heteroatom group that's going to come off. And the nucleophile would be this hydroxyl group over here. This oxygen would be a nucleophile would come in, and nucleophilically attached to that carbon and displacing, kicking off the OH leaving group. You can see that's going to make a ring structure. Stable ring structures are generally 5 and 6 membered rings. You can get 3-membered rings. They can form because things are close enough that they will kind of attach together. 4-membered rings are very strained and not common, but we did see a 4-membered ring intermediate in the last chapter. It was the that name reaction. That was the so-called Wittig reaction. So in this case, when you count atoms, that gives you a 5-membered ring. Let me go ahead and write out the structure now. All right, there we have it. It's a 5-membered ring. This is a cyclic anhydride, and of course water as a byproduct. All right, let's go to the next assignment. Okay, this is assignment 21-3B, the second assignment number 3. So those two probably have related reactions. Let's take a look. We got a carboxylic acid, one reactant, and then a methoxide. Okay, now be careful with this one. Carboxylic acids, always remember, they can undergo acid-base, nucleophilic substitution, etc. Could this be a nucleophilic substitution? You got to think carefully about this. It's sort of logical. You could say, oh, the OH is a leaving group. It's a heteroatom group. It breaks off and then it's replaced by OCH3. That's logical, but it's not correct. And you got to realize that if you mix an acid and a base, that's what's going to happen. It's going to exclude any other kind of reaction, and really that's what we have here. You have a carboxylic acid. It's a weak base, but you're reacting that with a strong base methoxide ion. It fits the Honk rule, and so you're going to have an acid base. You won't have a nucleophilic substitution. All right. So let me go ahead and write out the product of that. All right. Those are the products of the acid-base reaction. Carboxylic acid is acid that donates a hydrogen ion. The hydrogen ion bonds to the negative oxygen of the methoxide ion, and that gives you the products of the acid-base reaction that are shown. Let's say, look at reaction C. You've got a carboxylic acid reacting with amide ion. Could that be a acyl carbon substitution? Well, it's kind of like reaction A. It's logical. Think of OH coming off and replaced by NH2, but it's not that. Always look for acid base first. If you've got one thing as an acid and anything a base, it's going to be an acid base. That'll exclude all other possibilities, and that's what we have here. This is just an acid base reaction. So let me write out the products of the acid base reaction now. All right, there is the product of the acid base reaction. The NH2, the amide ion, is going to pull off an H+. That produces NH3. Take away an H+ from a carboxyl, you get the carboxylate. Reaction D, all right, carboxylate plus HCl. Looks like acid base to me, and so you can write the product of that. Just take the H off the HCl, bond it onto the oxygen, and that leaves chloride ion as a byproduct. Let me go ahead and write out the structures of the product for that reaction. All right, there it is. Reaction E. All right. So far, it looks like acid-base reactions have been the running theme. What about reaction E? Is that going to be an acid-base? Well, let's see. You've got an amide. That's a carboxylic acid derivative and water. Now, the hydroxide isn't really reactant. That's just gives basic conditions that make the reaction occur. It's basically a catalyst. So we don't want to invoke it as a reactant. Amide ion is extremely weak as an acid base. Water very weak at acid base. That's not going to be a significant reaction, acid base. For a significant reaction, you have to have one or both be strong, and neither are strong here. So that doesn't look like a good choice. Well, what other reactions can take place? So carboxylic acid, remember, mainly two reactions are reduction and acyl carbon substitution, a type of nucleophilic substitution. That's what's going to go on. That's what's going on here. NH2 is the heteroatom group that's going to break off. You're going to take it off. The OH from water provides is the nucleophile from water, and that's going to take the place of NH2. And so let's go ahead and write the product of that reaction. That's this acyl carbon substitution. All right, so applying the pattern, this looks like a type 2. The leaving group NH2 breaks off. It's going to bond to hydrogen from the water, produces NH3, the byproduct, and the OH from water is a nucleophile that goes ahead and attaches to the carbonyl group. So you get a carboxylic acid and ammonia as the products for this reaction. All right, the next reaction, carboxylic acid reacting. SOCl2, oh goodness, haven't seen that in a while. That's called thionyl chloride. In our study in the alcohol chapters, we saw it there. Now, could it be an acid base? Well, SOCl2 doesn't look like a base to me, so rule that out. Nucleophilic substitution. Well, let's come back to that. SOCl2, could that be a reducing agent? No, it's not. Not decarboxylation. And that's not also the HVZ, the type of halogenation reaction. The answer is yes, it really is a acyl carbon substitution. Now, you don't have to know the mechanism of this. I don't even remember if I discussed it, but it's similar to what happens when alcohols are converted to an alkyl halide. The OH gets replaced by sulfur species. And let's see. Well, let me correct my wording there. The OH, the oxygen of OH bonds to sulfur. That covalent bonding converts the bad OH leaving group into a good leaving group, and so that's the essence of that. The sulfur bonds to the oxygen, kicks out a hydrogen, and that produces that converts the OH bad leaving group into a good leaving group. Chloride ions a nucleophile, and that displaces that sulfur species. Kind of talking through what the mechanism is. But anyway, this is a reaction that produces an acyl chloride, and it is a type of acyl carbon substitution. So let me go ahead and write the products out for that. All right, there it is. Now, you don't have to worry about the sulfur byproduct, just the fact that the carboxylic acid converted to the carboxylic acid derivative, that is the acid chloride. All right, let's go on to the next assignment now. Okay, this is assignment number 4 for chapter 21. This assignment is all about the mechanism of the acyl carbon substitution reaction. So the instructions here have some clues. Let's read it over. It says, write the mechanism of each of the following reactions, and each reaction indicate the slow step. Now, it's very important when you write the mechanism of any reaction that you identify the slow step, assuming that it's a known. And always use curved arrows when you're showing the steps of a reaction. That's a very important drawing convention that chemists use worldwide. It shows what atom joins to what atom, what bonds get broken, and it really hones in on the important detail about how a bond is made or broken. Without it, you really, anyone is going to kind of struggle to piece it together, but it shows you in detail of what's happening. And so that's a good skill to develop, is drawing in the curved arrows for each step of the mechanism. It says that, number 1, you are encouraged to think about 2 things before you start to write out the mechanism. Ask yourself first, are the conditions base, neutral, or acidic? Because those basically define the mechanism that an acyl carbon substitution reaction is going to follow. Base neutral is one condition, acidic is another. Base neutral, well, I got to be careful generalizing. The steps, there's fewer steps in that. Under acid conditions, that's basically an acid catalyzed process. And in an acid catalyzed process, hydrogen ion attacks on early, and then the very last step, it breaks off. Okay. It says the next statement, based on the leaving group in the acyl carbon substrate, which step is rate determining? All right. So that's kind of the idea here. If in any of these substitution reactions, most of them, the departure of the leaving group is rate determining, unless the leaving group is so good that it's going to break off easily, and that's not the rate determining step. The best leaving group is the chlorine. So the mechanism for an acid chloride reaction, it's not the ejection of the leaving group that's rate determining. It's actually the attachment of the nucleophile to the carbon-no-carbon. That's essentially the first step. So that's something to keep in mind. Let's see here. In parentheses, ejection of the leaving group is always rate determining unless the substrate is an acyl chloride, in which case the attack of the nucleophile is rate determining step, and that summarizes what I just stated. Number 2, does the leaving group get protonated before it is ejected? And that's a very important thing to think about. Does the leaving group get protonated before it is ejected? The general answer is this. Under acidic conditions, the leaving group will always get protonated before the leaving group departs. Here's an exception, unless the substrate is an acyl chloride. Where a chloride ion is the leaving group, it's so base, it's such a weak base, it can't bond to a hydrogen ion, and so it's just going to break off by itself. So in acid conditions, the leaving group always gets protonated first, and then the ejection of that is rate determining unless it's an acid chloride. And addition step is the rate determining step. Now, under base neutral conditions, that's a little different. The leaving group will always leave without prior protonation unless the substrate is an amide. In which case, the amide, the nitrogen is leaving group, it can't leave by itself. It's too strong of a base. You have to provide a proton to it. And generally, that's the protonation comes from the solvent, right? So think about number 2 in a very general sense. Under acid conditions, the leaving group is always protonated unless it's an acid chloride. Under basic conditions, the leaving group is not protonated unless the leaving group is an amide. All right, so let's go ahead and take a look now. Reaction A is an acid chloride reacting with methoxide that's under basic conditions. Remember what we said under basic conditions, the leaving group will always be protonated unless it's a chloride, and that's a chloride. Reaction B is an ester undergoing hydrolysis. That's an acyl carbon substitution reaction. It's under acidic conditions, so there, of course, the leaving group will always get protonated unless it's a chlorine. And it's the ejection of the leaving group that is the rate determining step. And then C is an ester reacting with water. Look at the B and C, the comparison contrast. They're same reactants, one's under acidic conditions, the other under basic conditions. And so it's important to think through the difference there, and we're going to do that step by step. And then D is an amide reacting with water under basic conditions. And so remember the generalization under basic conditions. The leaving group is not protonated unless it's a nitrogen. And that's what we have here. And remember, ejection of the leaving group is always a rate-determining step unless it's an acid chloride, and it's not an acid chloride. All right, let's move down and look at I'm going to look at the answer sheet to make things a little easier. Okay, reaction A. All right, it's under basic conditions. We're not going to protonate anything. The attack of the nucleophile is the first step. That gives you a tetrahedral intermediate shown. Now remember, an acid, when you have an acid chloride, the addition step is going to be rate determining. So I've got that first step labeled slow. The second step is ejection of the leaving group from the tetrahedral intermediate. That's going to be a fast step, and that gives you the product, an ester. All right, so let's go to the next problem. Okay, so let's think about the conditions first. It's acid conditions. In the acid conditions, there's more steps. First step, the carbonyl oxygen gets protonated. The nucleophile attaches. You've got a proton shuffle step there where you basically have to attach proton to the leaving group. The leaving group is ejected, and then the last step, proton leaves. So let's follow through there. All right, so B, first step, detachment of hydrogen ion from the catalyst to the oxygen. All right, the protonated species here. Water, the nucleophile now attaches to the carbonyl carbon. It gives a tetrahedral intermediate shown here. And now the proton shuffle step. The leaving group is OCH3. It's got to bear a proton. You got a proton on it. So that happens in two steps. So H plus comes off the oxygen here, and in the second step it attaches to the methoxyl oxygen. And we're ready to launch off the leaving group. The leaving group is now protonated, and now it's going to eject. And this would be the slow step shown here: ejection of the methanol leaving group. Now we're one silly proton away from the final product. The very last step, the H plus catalyst comes off, gets regenerated, and giving you your final product here. Reaction C, all right, it's basic conditions. Hydroxide is going to attach to the carbon in the first step. Now here, this is the addition step. Here is not the step. Not the slow step. Slow step is the ejection of the leaving group that will leave by itself in this particular case. And so a lone pair from the oxygen swings in, and it kicks out the methoxide ion. And that ejection of the leaving group is a slow step, and there you have it. Reaction D, the amide reacting under basic conditions. Now, remember, basic conditions, leaving group always leaves by itself without prior protonation, unless it's a nitrogen. And nitrogen is such a poor, awful leaving group, it can't come off unless it's prior protonated. First step is going to be attachment of hydroxide to give the tetrahedral intermediate here. You do have to attach a hydrogen ion to the nitrogen. Where's it going to come from? Well, we can't add acid. That would no longer be basic conditions. It comes from the water. Water does provide the proton, and that protonates NH2. And now we're ready to launch off the leaving group. The carbonyl group, the lone pair and oxygen swings in to reform the carbonyl group. That pushes off an NH3, and that is now the slow step. And basically, we have our product now. All right. So mechanism is really important. I want everybody to kind of think through what's going on. This particular assignment is a good exercise. Let's go on to the next assignment. All right, 21-5. I'm just using two reactions here. We have an acid chloride reacting with an organometallic. A. In C, notice there's an ester reacting with another organometallic. The key here is to make a distinction between the type of organometallic. Remember, organometallics fall into category 1, category 2. Category 1 are those that include organolithium and Grignard. Those are the most reactive metals, lithium and magnesium. And category 2 include all other metals. And the thing to realize is that the category 1 is an order of magnitude more reactive than the others, and that has an impact on the reaction itself. In the case of reaction A, the acid chloride reacting with the dimethyl cadmium, you can write the dimethyl cadmium in its ionic form. Let me go ahead and do that. All right, there's the ionic form. The methyl carbanion breaks off from the rest of it. Methyl, the CH3 is minus, everything else is positive. All right, it looks like a nucleophilic substitution reaction. The chlorine is the leaving group, the heteroatom group it's going to break off, Cl. The nucleophile is the methyl carbanion it's going to attach. And that's going to give a ketone. I'll write out the structure. And here's the key. We learned in chapter 20 that ketones and aldehydes are subject to addition by the category 1 organometallics. But the category 2 are not reactive enough to affect addition. They will provide nucleophiles for an acyl carbon substitution if the derivative is sufficiently reactive, and acid chlorides they're reactive, they're the most reactive. So the key is that the ketone that forms doesn't go any further. It can't react with any remaining organometallic. It just doesn't have the oomph to do that. So this is a product of the reaction as a ketone. So let me write that out. All right, there's the product, the ketone product, and that stops there. The byproduct, that is the methyl cadmium chloride. All right, the chloride ion leaving group bonds to the methyl cadmium cation. Reaction C, now this is important to see the distinction. Notice there's 2 moles of a Grignard reagent. Grignard reagent is more reactive. And what's going to happen here, there's really 2 reactions, sequence 2 reactions. First, it's a nucleophilic, it's an acyl carbon substitution to give the ketone like we saw in reaction A. But then the remaining Grignard reagent is going to affect an addition on that ketone, the same reaction we saw in chapter 20. So it's going to be an acyl carbon substitution followed by addition. Let me go ahead and write out the product of that. Okay, ketone is the product of the acyl carbon substitution reaction. You've got an additional mole of Grignard that's going to effect an addition on the ketone. I wrote it in the ionic form. The methyl carbanion is going to come over here and bond to the carbonyl group, or carbonyl carbon. And then the oxygen here is going to bond to the electrophile, the Mg+, and that will produce then the magnesium salt. Let me write out the product structure. All right, there is the addition product of the Grignard methyl magnesium chloride adding across a carbonyl group. Now, if you just walked away, that would be the final product. You could isolate it if you wanted. Nobody does. Instead, of course, and this is indicated in the equation, you have here this step here. You're going to acidify, and basically that's just an acid-base reaction. The hydrogen ion that's provided in the acidic medium is just going to attach to that oxygen, and that's just going to give you an alcohol, a tertiary alcohol. Let me write out the product now. Okay, there it is, tertiary alcohol, and then the magnesium byproduct. Okay, let's go on to, I think this is the next thing we're going to do is the second page on assignment 5. So let me bring that up. Okay, this is question number 2 in assignment 21-5. Propose a synthesis of each of the following carboxylic acid derivatives, starting with a different and appropriate carboxylic acid derivative. Now, think about this kind of continuing theme in chapter 21. You could start with a carboxylic acid, and then you could carry out a reaction that converts it to a carboxylic acid derivative. You could take that derivative and convert it to a different derivative. You could take either of those derivatives and convert it back to the carboxylic acid. So there's a kind of a interconnectedness in that respect. To make a carboxylic acid derivative, there's two ways. Start with a carboxylic acid, or start with a different carboxylic acid derivative. Now, here's the key if you're going to convert one derivative to another. You want to start with a carboxylic acid that is more reactive than the product carboxylic acid. Now, we're going to talk about order of reactivity formally near the end of the video, but basically acid chloride is the most reactive, then comes acid anhydride, then ester, then amide. So let's just see. On question A, we want to make an ester. You'd want to start with either an acid chloride or an anhydride, something that's more reactive. So, and I'm showing the answers here. We're starting with an acid chloride. That would be sufficiently reactive. And you can kind of figure out that in order to make the derivative, you have to get an ethoxy nucleophile to take the place of the chlorine. Ethanol would do that. And you've got a type 2 acyl carbon substitution. The oxygen, it bonds to that. The chlorine comes off. And gives you the desired product here. All right, so, and then, reaction B, what do you start with? Amide is the least reactive, so you have a choice here. You could start with an ester, an acid chloride, or even an anhydride. I'm choosing to start with the ester. You can see that I got to get that amine group attached there because I want to make an amide. So taking the ester here and reacting it with this amine is the correct thing to do. So this heteroatom group comes off, is replaced by the nitrogen, and that would give you the desired product. All right, and then the next reaction, C, we've got to make an acid anhydride. We have to start with an acid chloride here, and that's what I'm doing. Start with an acid chloride. And what's the appropriate reactant? Well, we want to be able to attach a carboxylate to that, a carboxyl group. So the sodium carboxylate is the appropriate reactant to use, you can see, and piece all that together and you get the desired product form. All right, let's go to the last assignment, I believe. There's a couple of pages to that. Okay, this is assignment 6. So we have a carboxylic acid reacting with a reagent. What is the reagent? Well, lithium hydride is a reducing agent. Especially at this point in your study of organic, you've certainly come a long way. You've encountered all of the important oxidizing and reducing agents. I think the list is pretty complete. So you might make a list of oxidizing and reducing agents. Lithium hydride is the reducing agent. Sodium borohydride. Ask this question: which is more reactive, the lithium aluminum hydride or the sodium borohydride? The answer is the lithium aluminum hydride, sometimes abbreviated LAH. And so now, carboxylic acid, we talked about this in the intro. Carboxylic acid is reduced to an alcohol. Now you've got to use the more reactive lithium hydride. The sodium borohydride wouldn't do anything except a acid-base reaction, and that's it. So when you do that, of course, you're going to get the primary alcohol. Let's go down to the next one. That's the acid chloride with the sodium borohydride. Acid chloride is so reactive, you can get by with the sodium borohydride, which is not as reactive as the lithium hydride, and that's sufficiently reactive to affect a a reduction that goes all the way to the alcohol. So alcohol is a product for A, for C. Now we've got an ester reacting. Esters, carboxylic acid, like carboxylic acids, undergo reduction. All right, and they generally reduced using the appropriate reducing agent to the alcohol. The exception is the amide. The amide reduces to an amine. So on reaction D, that's going to produce a primary alcohol. Reaction G, there's the amide, and that's the exception. So let me go ahead and write out the products of all of those reduction reactions. All right, there are your products. Reaction A is a primary alcohol. Reaction C is a primary alcohol. Reaction D, primary alcohol. Now the switcheroo, the exception. Amide ions don't reduce to primary alcohols. What happens there is the carbonyl group gets reduced to a methylene group. The nitrogen stays attached. And so when amides reduce, they reduce to amines, not primary alcohols. All right, let's go to, I think it's just one more, it's part 2 of assignment 6. All right, now, so we have, looking over the reactions here, it looks like the reactant is a carboxylic acid in every case. A, B, F, H have heat, no other reactant. And what is apparently happening now is the heat itself provides sufficient energy to make the reaction happen. It's the carboxylic acid is a single molecule reactant. What could that be? Well, decarboxylation. We talked about that in the intro. If you just take a carboxylic acid, ordinary monocarboxylic acid, and heat it even to high temperature, nothing would happen. It probably would undergo decomposition just from the high temperature, but decarboxylation occurs on an activated carboxylic acid. The activation consists of one of the so-called 3 amigo groups attached to the alpha carbon. The alpha carbon is the carbon to which the carboxyl group is joined. And that's the key here. So I did discuss the mechanism in the video lecture. It goes through an internal hydrogen bonded species. With high temperature, bonds get made and broken, and you break off a CO2 molecule. This question is not asking for the mechanism, however, but let's take a look here. Reaction A, is it properly set up to do the thermal decarboxylation? Do you have one of the 3 amigo groups attached to the alpha carbon? Well, yes, you do. All right, so you got... well, here's the alpha carbon, all right. Attached to the alpha carbon, you've got a carbonyl group, one of the amigo groups. So yes, that's going to affect the decarboxylation. So we can go ahead and write that out. Now, decarboxylation, the carboxyl group itself breaks off CO2. Hydrogen takes its place, so you're going to write as the product there, the decarboxylation product, this ketone, byproduct of CO2 gas. All right, and now we've got B, is it set up for thermal decarboxylation? Is there one of the amigo groups attached to the alpha carbon? Right, the alpha carbon atom is right there. Okay, well, my pen's not working. Just a moment. All right, there it is. All right, the alpha chloro product. Okay, now let's look at F. Well, carboxylic acid by itself, heat, looks like potentially a thermal decarboxylation. But be careful now. It has to have one of the amigo groups attached to the alpha carbon. Short of that, it won't thermally decarboxylate. This one's a little tricky, just in my experience of giving this question to students. Many trip up on it. Let's take a look. There's the carboxyl group. Where is the alpha carbon? Well, it's right there. It's the carbonyl carbon. But wait, the carbonyl group is an amigo group, but the carbonyl group has to be attached to the alpha carbon. It itself cannot be the alpha carbon. So that doesn't fit the pattern, and so there's really no reaction for F, no reaction. All right, there we go, no reaction for F. All right, let's take a look at the next problem. Reaction H. It's a dicarboxylic acid. This might be a puzzler. The way to think about it is that one of the carboxyl groups potentially can be the group that eliminates CO2. So we could kind of, circle that right here. Now that's potentially, the one that's going to see a breaking off of CO2. All right, where's the alpha carbon? All right, well, right here, oops, excuse me, no, I made a mistake. This is the alpha carbon right there, all right, there. Do we have an amigo group attached to the alpha carbon? No nitro or cyano, but this, the carboxyl group provides a carbonyl, which is the amigo group. So yes, this is going to decarboxylate, and we can go ahead and write the structure of the product here. And for emphasis, there would be a hydrogen here. And of course, the inevitable byproduct, CO2 gas. All right, so there you go. Now, I think that's all. I see there's question 2. I don't think, well, let's see. Wait a minute. Maybe, am I doing anything with question 2? Let me pause the video and take a look. Okay, I looked, and this is pretty much all there is. To finish this video, what I want to do next is to talk about the relative reactivities of the carboxylic acid derivatives. So let me go to some notes I have for that. Okay, here we are. Now, there's 4 representative carboxylic acid derivatives. Acid chloride, starting on the left, acid chloride, the anhydride or acid anhydride, then the ester, and then the amide. There's one that I have kind of omitted, and that's the thiol ester. I'm not specifically talking about it, so we'll just consider these 4. It's important to realize that with respect to the acyl carbon substitution, there's a relative reactivity, and that's shown in the slide here. The most reactive is the acid chloride on the far left. The least reactive is the amide on the far right. Okay. So it's important that you know this relative reactivity and explain why it's followed. Fundamentally, it's the ejection of the leaving group that is the rate determining step. What I've done is to draw the structures of the leaving group for each of these. The acid chloride, the leaving group is chloride ion, shown there. And then the leaving group for the anhydride is the carboxylate. Okay, and shown as a second species. For an ester, the leaving group is the ethoxide ion, and the leaving group for the amide is the, well, in fact, it's called amide ion, N-. Now, on the basis of their base strength, you have the rule that the most strongly basic is actually the least stable. That's with respect to, say, bonding to a hydrogen ion. The most stable one is in fact the least basic. So chloride ion, if you look at the base strength, chloride ion among all these species is the weakest base. In fact, it's so weak it doesn't even have observable base behavior. The strongest base is the amide ion at the far right. Now, leaving group ability is correlated with species stability. And I've just indicated here, the most stable of these leaving groups is the one that's just the weakest base, and that would be the chloride ion. The least stable leaving group is the one that has that is the strongest base, the most basic. So if you look at that correlation, leaving group ability correlates with species stability. A leaving group is better if it's more stable. It is poorer if it's less stable. So you can see that now the best leaving group should be the chloride ion, which is the most stable and least basic. The worst leaving group, the poorest leaving group, should be the amide ion, which is the strongest base and the least stable. All right, and so that fundamentally accounts for how a difference in reactivity of these carboxylic acid derivatives. Their activity is dictated by how good the leaving group is in the acyl carbon substitution. The one with the best leaving group, that's the most reactive. The one with the poorest leaving group is the least reactive. You can see maybe with a multiple choice question that could be coming up. I give you 3 or 4 representative carboxylic acid derivatives. The question is which is the least reactive or which is the most reactive. We might have a group of 3 of these, which is the most reactive or which is the least reactive. Okay, that concludes the video. I'm going to piece it together and render it. Time-wise, how are we doing? It's a little after 5:30, so I'm going to post this hopefully between 6 and 7. It takes time to render it, not that long to actually post it. I'm not posting this on YouTube. I'm just going to post it right on Moodle. And so hopefully this will help with your understanding of the material and helping you to score better on the quiz. Have any questions, you know where to find me. Take care now. Goodbye.